In this video, I want to talk about the concept of partial melting, which is probably a concept that's not very familiar to you. I'm going to be showing how different kinds of materials melt using a graph. So on the graph here, I've got temperature on the x-axis increasing from left to right, and the y-axis consists of the percentage of the original material that is melted, ranging from 0% to 100%. You'll see why I express it in that way in a second. So let's start out with a simple substance, one that you're familiar with, something that's really simple, like, let's say, like water. Okay, so H2O, and we're going to start out with solid H2O or ice. And we know that that solid H2O or ice will melt when we raise the temperature to 0 degrees C, right? So if I start the material, if I start at a temperature lower than that, and I slowly raise the temperature, what this graph will look like is this. It'll sort of climb up towards its melting temperature, and then at its melting temperature, it will instantly melt. So at a single temperature, it will melt, and then at all higher temperatures, it will exist in the liquid state. And that's the way familiar, simple chemical substances melt. Rocks, however, are not simple chemical substances. They've got lots of different components, at least 7 or 8 major components and many more minor components. And under those conditions, they melt in a very different way. So let's talk about how a typical rock would melt. So once again, using the same axes here, we're going to start with some rock that's a solid rock, and like right over here, and we're going to allow it to start to heat up. And as we do so, the rock will heat up until it reaches what we call it's sort of its first melting temperature. I'm going to mark it right like this. And at this point, at higher temperatures, the rock begins to melt but doesn't melt entirely. In fact, the diagram looks like this. So at the first melting temperature, the rock begins to melt, but melting isn't completed until we reach a second melting temperature. And above that second melting temperature, this one over here, the composition will be entirely liquid. We call these two melting temperatures, they have special names. The lower melting temperature is called the solidus, and the upper melting temperature is called the liquidus. And these two temperatures are actually quite far apart, about 200 degrees apart under typical conditions. So there's a big range of temperatures over which both solid and liquid are thermodynamically stable at the same time. And this is what makes rocks here different than simple materials like H2O. They have a range of temperatures over which both the solid phase, the rock, and the liquid phase, the magma, are both stable. And it's not until we exceed a higher liquidus temperature that the rock becomes completely melted. Now, I want to do one other thing on this diagram, which is on the same diagram, the same x-axis. I want to express the composition of the liquid on a separate y-axis. So the y-axis is going to extend from higher values meaning more felsic, more silicon and sodium and potassium, and lower values meaning more mafic, more iron and magnesium. And I can show then how the composition of the liquid is going to change during this process of partial melting. So for reference, let me first put on here the composition of the original rock. So this horizontal line here represents the composition, whatever it is, whatever its composition on the mafic, felsic continuum scale is, the composition of the original rock. And what I'm now going to plot in red here is the composition of the liquid that's produced when that rock passes the solidus temperature, rises to temperatures above its solidus temperature. And this is what it looks like. So here's what the composition of the liquid looks like. And notice what happens. When we first cross the solidus, as we raise the temperature above the solidus, and a small amount of liquid is produced, it has a composition that is significantly more felsic than the composition of the original rock. And as melting proceeds and we get closer and closer to the liquidus temperature, that composition becomes progressively closer and closer to the composition of the rock. And when we reach the liquidus temperature, the composition of the liquid is exactly the same as the composition of the original rock, which, if you think about it, has to make sense, right? If we start out with the original rock and we melt it completely, it's a closed system, so both of those things will have to have ultimately exactly the same composition. The important thing, though, to recognize is that initially when melting starts, when we cross the solidus temperature, it's the felsic components in the rock that melt out first, the silicon and the sodium and the potassium. And so the liquids that are produced just above the solidus are more felsic than the original rock. Now here's the thing. In reality, most rocks melt to about between, say, 20 and 50% of the way between the solidus and the liquidus. In other words, they end up being between 20 and 50% partially melted. So if we can sort of show that on this diagram with this sort of purple band like this, that represents the typical range of melting for rocks. And if we look at this, we can see that that corresponds to liquids which are somewhat more felsic than the original rock. And in fact, the rule of thumb, in which I've talked about in other contexts, is that the liquids generated by between, say, 20 and 50% partial melting are one step more felsic than the original rock. So in other words, if the original rock was mafic, then those liquids will be intermediate. If the original rock was ultramafic, then those partial melts produced by between 20 and 50% melting will be mafic, one step more felsic than the original rock. And this diagram shows how that's true. Notice also that that's very much an approximation, right? If you had, for example, 90% partial melting, then the liquid in the rock would have almost exactly the same composition. And if you had an extremely small percentage of partial melting, like 1%, then we'd expect to generate liquids that are a good bit more than one step more felsic than the original rock. But in most cases, rocks melt about 20 to 50%, and under those conditions, the liquid they produce will be approximately one step more felsic on the 4-part mafic to felsic scale than the original rock.